Hello everyone, welcome to this lecture series on Laplace transforms. In the previous lecture, we talked about the definition of Laplace and the sufficient condition for the existence of this transform, and we also discussed the transform of some elementary functions. Today, we are going to talk about the properties of Laplace transform. And once you remember these properties along with those uh, elementary result, then you can uh, find the Laplace of most of the functions for which the Laplace actually exists. Okay, so we are going to discuss 7 properties today, and the first property is the linearity, and it says that Laplace of a times function of t plus b times function of g function of t is equal to a times Laplace of ft plus b times Laplace of gt. That means it says that Laplace of sum of functions is same as sum of individual Laplace. Okay, so by linearity we can uh, separate the Laplace of sum into sum of individual Laplace, and then if we know the result for individual Laplace, then we can have the Laplace of sum. Okay, so the proof of this is very simple, that we start with the left hand side, that the Laplace of this function, by definition Laplace of any function. So here a times f function of t plus b times g function of t is a one function. So Laplace of this is integral 0 to infinity of the function time e raised to power minus st dt. Here a and b are constants. Okay, and so we know this in that in integrals the integral of sum is sum of integral where constant goes outside. Okay, so this can be written as a times integral 0 to infinity ft e power minus st dt. Okay, so a times ft e power minus st dt plus b times gt e power minus st dt. Okay, and because this first integral is Laplace of ft, so we can write this as a times Laplace of ft function plus b times this is a Laplace of gt. Okay, so we can write that it is a times Laplace of ft plus b times Laplace of gt. Okay, so this is the first property, that we can uh, compute the Laplace of sum of functions as sum of their individual Laplace. Okay, so for example, say if we have to find the Laplace transform of this function, where function is 2 e power 3t plus 7 times sine 2t minus 4 times cos 5t, then the Laplace of this whole function will be equal to, by this rule, Laplace of first function plus Laplace of second function plus Laplace of third function. And because we know the Laplace of exponential, Laplace of sine, Laplace of cosine, so we will have the result easily. Okay, so just to add that in the last lecture we said that the Laplace of e power at is 1 over s minus a, Laplace of sin at is a over s square plus a square, and Laplace of cos of at is s over s square plus a square, where a here is a constant. Okay, so in the first case is 3, in the second sine it is 2, and in the cosine it is 5. Okay, so Laplace of this whole function by linearity it is 2 times Laplace of exponential plus 7 times Laplace of sine function and minus 4 times Laplace of cosine function. And because Laplace of exponential is known, okay, with a value 3, so its Laplace will be 1 over s minus 3. Okay, similarly Laplace of sine 2t, so if you compare with this a2, so Laplace will be 2 over s square plus 4, and Laplace of cos 5t, so if I put 5 here, so it will be s over s square plus 25. Okay, so easily we can write the Laplace of each, and so we have a result. Okay, so Laplace of this function is given by this result. Okay, so linearity is important. Okay, one of the important properties, we can separate the sum of functions to Laplace of individual. The second property is the S shift or first shift, and it says that if you know the Laplace transform of any function ft and its value is say fs, okay, where fs is of course calculated from this integral 0 to infinity ft e power minus st dt, then Laplace of e power at ft, okay, will be f of s minus a. That means if we multiply the function with the exponential e power at, then the Laplace of this product will be the shift of s to s minus a. Okay, so let us prove this first. So the Laplace of e power at ft, this left hand side, okay, so by definition Laplace of any function is integral, so Laplace of e power at ft will be 0 to infinity e power at ft e raised to a minus st dt, and because this first is exponential and this third is exponential, so these two can be combined, so we can write it as 0 to infinity ft e power minus s minus a of t dt. And if you compare this with this integral, then only difference is that here this parameter s becomes s minus a, so obviously this integral will here will impact that s will replace with s minus a, so the value of this will be nothing but f of s minus a. Okay, so if you know the Laplace of ft as fs, then the Laplace of exponential time ft will be nothing but the s will shift to s minus a if the a here is given. Okay, so for example, say find the Laplace transform of 2 e raised power 3t sine 2t. Okay, so if you know the Laplace of sine, then we can use the first shift or s shift, that multiplying with exponential means s will replace with s minus 3, as a is 3 here, right? So first we will write the Laplace of 2 sine 2t, and then we'll use this property of s shift. We will add, multiply or add exponential there. So we know Laplace of sine function, sine at is a over s square plus a square. So Laplace of 2 sine 2t, by linearity 2 goes outside, and Laplace of sine 2t will be 2 over s square plus 4. So 2 into 2 is 4, so 4 over s square plus 4. And then multiplying with this exponential, so Laplace of this whole function will be the s will shift to s minus 3, so s minus 3 in the denominator will get. Okay, so the Laplace of this function will be that the s will shift to s minus 3. Okay, so this function is my fs, okay, Laplace of ft, and then multiplying this means f s will become f of s minus 3. So take one more example here. Say find the Laplace transform of this product t raised to power 7 e raised to power 5t. So again I can use this as shift because one of the function is exponential. So if I know the Laplace of t power 7, then I will use first shift by adding this exponential. So t power 7 is a polynomial, and we know the Laplace of t power n, that it is gamma function of n plus 1 over Sn plus 1. Here n is integer 7, and whenever n is integer, gamma function of n plus 1 is n factorial. Okay, so Laplace of t power 7 will be gamma function of 8, which is nothing but 7 factorial, so 7 factorial over s power 8, and then multiplying with exponential means this shift. Okay, so s will replace with s minus 5. Okay, so Laplace of t power 7 e power 5t is nothing but s factor 7 factorial over s minus 5 power 8. Okay, this s is replaced with s minus 5 because of this s shift property. So this was second property, the s shift. Okay, whenever there is exponential multiplied to function, if we know the Laplace of function, then the Laplace of this product is s replaced with s minus a. Okay, property 3 is change of scale. Okay, so again it says that if Laplace of function is known, okay, Laplace of ft is fs, where fs is this integral, then the Laplace of function of at, okay, so the scale of t is changed to a times t, is equal to 1 by a f of s by a. So we multiply the we change s to s by a, and the whole answer is multiplied with 1 by a. Okay, so let's prove this now. we know the Laplace of f of a t by definition. Okay, Laplace of any function is integral 0 to infinity that function into e power minus st dt. Okay. Now to prove this, we just substitute at as a new variable u. So if I put at as u, then t will be u by a and dt will be du by a. So we'll just put it here. So at will be u, dt will be du by a, and here in the exponential, this t will become u by a. Okay. The limits when t is 0, u is 0. When t is infinity, u is infinity. Okay. So limit remains same, u to 0 to infinity. Okay, here at becomes u, this t is substituted as u by a and dt will be du by a. Okay, so 1 by a is a constant, it goes outside. Okay, so 1 by a goes outside, and now this integral is very similar to this integral except that s parameter is written as s by a, so this function should be written as a function of s by a. Okay, so this property, third property, that if you know the Laplace of any function, then the change of scale, that the function of at will be 1 by f of s by a. Okay. Say for example, if you are given that the Laplace of a function is e power minus s divided by s, then find the Laplace of this function. Okay. So in this function, ft is scaled to function of 3t, and then this function is multiplied with the exponential. Okay, so we have to use change of scale. Okay, ft is changed to f of 3t, and then we will use s shift. Okay, multiplying with exponential means first shift. Okay, so Laplace of f of 3t, if we calculate that by using this rule, then that means 1 by 3 times, wherever s is there, s will become s by 3. Okay, wherever s is there, s becomes s by a. So Laplace of a function of 3t is nothing but 1 by a, which is 1 by 3, and in the fs, this is fs, s is replaced by s by 3, so e raised to power minus s by 3 and s by 3, so 3 cancels out and we have this. Okay, and then Laplace of exponential times this function, so we have a s shift, s will be replaced with s plus 2 because a is minus 2 here, so s minus a means s plus 2. So Laplace of this exponential time f function is nothing but e raised to power minus of s plus 2 by 3 over s plus 2. Okay, so in this way we can use the property together with the elementary results. Okay, fourth property is the Laplace transform of the derivatives of function. Okay, so if you know the Laplace of ft as f is, and the first derivative of function is continuous, then the Laplace of the derivative function is sfs minus f0. Here this fs is means Laplace of ft, and this f0 is function value at 0. Okay, so f value at t0, provided that limit t tends to infinity, e raised to power minus st ft is 0. Okay, so this is this property is nothing but will hold whenever this function is of exponential order. Okay, if it is of exponential order, it is always less than equal to some m e raised to power alpha t. Okay, so those exponential will combine and this will tend to 0 whenever s is greater than alpha. So this condition says that a function has to be of exponential order for this. Okay, let us prove this result. Okay, so Laplace of f dash t, the left hand side, and we'll prove right hand side. Okay, so Laplace of f dash t, by definition Laplace of any function is integral 0 to infinity e raised to power minus st, that function time dt. Here we can apply integration by parts, exponential as first function and f dash t as second function. So first function into integral of f dash t, which is ft itself, limits from 0 to infinity, minus integral derivative of first, so e raised to power minus st, its derivative is minus s e raised to power minus st, and integral of second, so that's ft dt. Okay, so here we have to substitute upper limit minus lower limit, so limit t tends to infinity on this minus limit t tends to 0 on this. Okay, So at t0 e raised to power 0 is 1 and f0. Okay, so we'll get minus of f0 and limit infinity. Okay, I'll just put, so limit upper limit minus lower limit 0 substituted, which is f0, and here minus s goes outside, so it becomes plus s, and rest is e raised to power minus st ft dt integral, which is Laplace of ft or fs. So immediately we get this result that sfs minus f0, this result provided this term is 0, provided this equal to 0. Okay, so this is our fourth property, that the Laplace of first derivative is sfs minus f0, uh, provided function is of exponential order and the first derivative is continuous. Okay, this property can be extended for higher derivatives. So the generalization of this, that if Laplace of ft is fs and the first n minus 1 derivatives are continuous, then the Laplace of nth derivative f n t, here n in bracket means nth derivative of this function with respect to t, so it will be equal to s power n fs, here fs means Laplace of ft, minus sn minus 1 f0 minus s power n minus 2 first derivative at t0 minus s power n minus 3 into second derivative of function at t0 minus so on the n minus first derivative of function at t0. Okay, so you can remember this result. Okay, the power of s goes on decreasing with 1. Okay, first is Laplace of function minus this product f0, then first derivative, second derivative, so on. Okay, this equation. So this property is very important in the sense that it will be used when we will solve differential equations using Laplace transform, because the property is on the derivatives, and the key is that it converts ordinary differential equation into algebraic equations. Okay, so the derivatives in t are converted into polynomial terms as power n into fs. Okay, so the differential equation will be converted into an algebraic equation by applying Laplace transform. Okay, so remember this result, Laplace of derivatives. Okay, and we will utilize it after maybe two lectures, once we will do Laplace of differential equations. Property 5 is multiplication with t power n. Okay, so it says that if Laplace of any function is known as fs, then Laplace of t power n times ft. Okay, so the function is multiplied with the t power n, then its Laplace is minus 1 raised to power n into nth derivative of fs, where fs is known as Laplace of function. Okay, where n is 1 2 3 so on. Okay, so if Laplace n is 1, that means tft, it will be minus first derivative of this. If n is 2, it is t square ft, and here it is positive 1 second derivative of fs, and so on. Okay, so let us prove this result also. So again we start to prove this by mathematical induction, and for that we'll first prove this result for n is equal to 1, and then we'll assume that it is true for n is equal to m, and then we'll prove it for n is equal to m plus 1. Okay, so to prove this for n is equal to 1, first we'll write the definition of what is f is. Okay, Laplace of ft, that is equal to an integral. Okay, so by definition f is, the Laplace of ft is nothing but this integral 0 to infinity e power minus st ft dt. Okay, and we differentiate this one time with respect to s on both sides. So if we differentiate this with respect to s, then left hand side will be derivative of f is with respect to s, and right hand side will be derivative with s of this integral, and because the integration is with t and derivative with s only on this. Okay, so derivative will give when applied on this exponential, it will become exponential function into derivative of minus st with this, so there will be minus of t, so minus t e power minus st is the derivative of this exponential with this, and minus sign goes outside, and then it is 0 to infinity exponential time tft dt. So by definition it is nothing but Laplace of tft. So immediately we have the result that Laplace of t times ft is, this minus sign goes to other side, is minus d ds of fs. Okay, so Laplace of tft is minus derivative of fs with this. So this proves the result for n value 1. Okay, so let us assume that the result is true for n is equal to m. That means the Laplace of t power m ft is minus 1 raised to power m and mth derivative of fs. Now to prove that result is true for n is equal to m plus 1, we differentiate this result with respect to s one time on both sides. So differentiating this equation with respect to s on both sides. So this right hand side minus 1 raised to power m is constant. So 1s derivative means this derivative will become derivative m plus first derivative of fs. Okay, so minus 1 raised to power m plus 1 derivative of fs, and on the left hand side it is derivative with s of this Laplace, so derivative with respect to s of Laplace. And by definition Laplace of any function is integral, so we can write this into integral form, 0 to infinity e raised to minus st t power mft dt. So again this derivative will be applied on this exponential, so it will give minus t e raised to power minus st, so the minus sign goes outside and t will become t into t power m become t power m plus 1. And so again by definition this is nothing but Laplace of t power m plus 1 ft. So this proves our result for m plus 1, that Laplace of t power m plus 1 ft is minus 1 raised to power m plus 1 into m plus first derivative of f is. Okay. So this fifth property. Okay, I'll take example on this property, that say find the Laplace transform of t square e power 5t. Okay, so here there is a product of polynomial with exponential, so you can also use first shift. If you know the Laplace of t square, then you can apply s shift by multiplying with exponential. So I'm just reminding you of property 2, that Laplace of t square is 2 pi s cube. So by s shift Laplace of t square e power 5t, and the s will be replaced with s minus 5, so 2 over s minus 5 whole cube. So the Laplace of this should be 2 over s minus 5 cube, but we are just going to find this solution by multiplication of t power m, where m is 2 here. So we will find first the Laplace of exponential and then multiplying with t square. So we know the Laplace of exponential, e power 5t is 1 over s minus a, so 1 over s minus 5. Okay, so Laplace of e power at is 1 over s minus a, okay, a is 5 here, and then this property then multiplying with t square, so it will be uh, minus 1 raised to power 2, because t power 2 is there, and then second derivative of this f is, okay, so 1 over s minus 5. So we'll differentiate this two times. Okay, so on differentiating two times you will see that the results are same. Okay, so that means we can apply Laplace on this function and then apply the property of multiplying with t square, or we can find the Laplace of t square and then we can use the property of multiplying with an exponential. Okay, so either way it gives the same result. Okay, so you should not be worried about using a particular rule. Okay, so given any function you just see what properties can be applied and what function we can start with. Okay, so I take one more example. Say find the Laplace transform of product of three functions t e power minus 3t sine 60. Okay, so we know first shift exponential multiplication. Now we also know multiplying with t. Okay, so if we calculate the Laplace of sine 60, then we can use first shift and then the polynomial multiplication, or write the Laplace of sine 60, then use polynomial multiplication and then use first shift. Okay, so either way you will get the same result. Okay, so first Laplace of sine 60. Okay, So Laplace of sin 80 is a over s square plus a square. So a is 6 here. So 6 over s square plus 36. Okay. So this result. Now you can use multiplication with t and then first shift, or you can use first shift and then multiplication with t. That's up to you. So here I am using multiplication with t first and then I will use first shift. So multiplying with the t power 1 means minus 1 power 1, so that's negative sign, and first derivative of this f is, so one derivative of 6 over s square plus 36. Okay, so denominator into derivative of above, which is 0, minus 6 time derivative of denominator, which is 2s, over denominator square. Okay, so minus 12 s over s square plus 36 square into minus sign, which is outside, so it becomes plus sign here. And now multiplying with exponential means first shift, so s will replace with the uh, s minus a, and a is minus 3, so s will be replaced with s plus 3 everywhere in this last result. Okay, so Laplace of this product will be s replaced with s plus 3 in this, so 12 times s plus 3 over s plus 3 square plus 36 whole square. Okay, so now I move to next property, and this sixth property is the Laplace transform of integral of function. Okay, so it says that if Laplace of ft is fs, then the Laplace of this finite integral 0 to t of ft dt is 1 by s fs. Okay, so if you know the Laplace of ft as fs, then the Laplace of integral of ft, where integration is from 0 to t, is nothing but the function is, whole function is divided by s. Okay, so 1 by s f s. Okay, so now we are going to prove this result. Okay, so for proof, let this integral be equal to phi t. Okay, so let phi t be 0 to t f t dt. Okay, so if I differentiate this with respect to t, then the derivative of phi t will be ft, and also phi of 0 will be 0, because if I put t 0 here, then integral is 0 to 0, so integration at a point is 0, right? Phi 0 0. Let us take the Laplace of this equation on both sides. So Laplace of ft, which is fs, and Laplace of derivative, and we know the rule for Laplace of derivative. Okay, and assume that Laplace of phi t is phi s. Okay, so this symbol for Laplace of phi t. So Laplace on both sides of this equation, so Laplace of ft equal to Laplace of this derivative, and by derivative rule, Laplace of derivative of a function is s times phi s minus phi 0. Okay, and phi 0 is 0, so this last second term is 0, so it is nothing but s phi s, and phi s is nothing but Laplace of phi t. Okay, so we can calculate Laplace of phi t as 1 by s of Laplace of ft. Okay, and that's our result, because phi t is this integral, we can put phi t back here as integral, and Laplace of ft is nothing but fs, so 1 by s fs. Okay, so this we can just rewrite this into this form. Okay, phi t is integration of this. Okay, and Laplace of ft is fs. Okay, so 1 by s fs, so this result. I'll take one example on this, that find the Laplace transform of this integral 0 to t e power minus t cos t dt. Okay, so here it is simple that first you write the Laplace of cos t, then you use s shift, and then you use this integral result, that whatever is the result for the ft function, that means e power minus t cos t function, that will be divided with 1 by s. So we know here that Laplace of cos of t is s over s square plus 1. Okay, by elementary result. Then first shift, multiplying with exponential, so s will be replaced with s plus 1 everywhere, because a is minus 1. Okay, and then this integral property, that Laplace of integral, if inner Laplace is known, is nothing but 1 by s fs. So fs is this one here, so 1 by s of this. Okay, so Laplace of integral is 1 by s of this whole result. Numerator is s plus 1 and denominator is opened into s cube to s plus 2. Okay, this part. And so finally, I'm going to give you the seventh property, that is division by t. Okay, and it says that if Laplace of ft is fs, then the Laplace of ft divided by t. Okay, so if divide the function by t is integral s to infinity fs ds, provided that this integral exists. Okay, so remember the limit is from s to infinity. Okay, of fs is Laplace of ft. Okay, so let us prove this result also. We know that fs is Laplace ft, and this is nothing but integral 0 to infinity e power minus st ft dt. Okay. So to have integral of this form, we integrate both sides of this with respect to s from s to infinity. Okay. So integrate this result on both sides with respect to s from s to infinity. Okay. So what we have is integral s to infinity fs ds on left hand side, and a double integral s to infinity of this ds. Okay. Here the inner integral is with respect to t and limits are 0 to infinity. Okay. And outer integral is with respect to s and limits of s are s to infinity. To t and s, they are independent variable. Okay. T limits are constants and s limit depend only on s. So we can interchange the order of integration without affecting the limits. Okay, so we can take s inside and t outside. Okay, integral. Okay, so if you remember the change of order of integration. Okay, so integration inner will be with respect to s and limit remain s to infinity, which were here outside. Okay, and outer integral is with t and limit is 0 to infinity. Okay, this happened because they are independent. Okay. So inner integral is with respect to s now, and ft is a function of t. So ft function can be written outside the inner integral. So I'm writing ft here. Okay. Now the inner integral can be solved. Okay, integration with s of exponential function. So exponential function integral is exponential divided by the derivative of this part minus st, which is minus t. Okay, because derivative will be with respect to s. So this will give the integral of this will be e raised to power minus st over minus t, and limits are s to infinity, and remember limits are for s. Okay, so upper limit s equal to infinity, when substituted it is 0. Okay, the exponential will become 0, and the lower limit is s value s. So when s value is substituted s, it remains the same exponential with the lower limit, so a minus sign will come, so this minus minus become plus. Okay, so it becomes ft by t e power minus st dt, integral 0 to infinity, and by definition this integral is nothing but Laplace of ft by t. Okay, so we have the result. Okay, Laplace of ft by t is integral s to infinity fs ds. Okay, take one example on this, that find the Laplace transform of this function 1 minus e power t by t. Okay, so there is a division by t here. So if you know the Laplace of 1 minus e power t, you can use this rule of division by t. Okay, and Laplace of 1 minus e power t we know. Okay, we just need to use linearity here. Okay, so Laplace of 1 minus e power t, by linearity it is Laplace of 1 minus Laplace of e power t. Laplace of 1 is 1 by s, Laplace of e power t is 1 over s minus 1. Okay, and then division by t means the integral of this result with from s to infinity. Okay, so Laplace of this function divided by t is integral s to infinity of this fs. Okay, fs is 1 by s minus 1 over s minus 1. Okay, so integral of 1 by s is log s, of this is log of s minus 1, limit s to infinity. Okay, so we'll, before substituting limit, combine logs. Okay, so it is log of s over s minus 1. At infinity it is 0, and at s it remains same with a negative sign for the lower limit, and the negative sign will reverse the numerator and denominator. So log of s minus 1 by s. Okay, so this is the Laplace of 1 minus e power t by t. So these are the 7 properties that you need to remember, along with the 7 elementary result, and these 14 results in total will help you find Laplace transform of most of the functions. Okay, so we'll continue with this, and in the next lecture we'll talk about inverse Laplace transform, and once we'll complete this, then we will take applications on how to solve differential equations using Laplace transform. Okay, have a very good day.